Grounding methods for electrical services are crucial for safety and proper operation. Let's examine the grounding practices for a main electrical service, an auxiliary service for emergency lighting and power, and a fire pump service. For the main service, which is 480/277 volts and 2000 amps supplied from a utility transformer using 6 sets of 4 600 mcm cables and 4-inch conduit grounded at the service entrance switchboard to a ground rod using a 4/0 ground and a 1/500 mcm at the main water pipe, the grounding methods are generally acceptable. However, using a 1/500 mcm as a supplemental grounding electrode conductor at the main water pipe is not ideal. It might not provide sufficient grounding capacity. For the auxiliary service, which is 480 volts, 3-phase, 3-wire connected to an indoor 45 kV ampere, 480 volts to 208/120 volts lighting power transformer, tapped at the utility transformer using 3 number 3 wires and 1 number 8 ground in a 1-inch conduit, it is recommended to establish system grounding, even with an extended ground wire from the transformer grounding system. This redundancy ensures a reliable grounding path in case of a fault. The fire pump service, which is 480 volts, 3-phase, 4-wire connected to a fire pump and jockey pump, both with disconnects and controllers, fed from the utility transformer using 3 number 3/0 wires and 1 number 4 ground in 2-inch conduit, with the jockey pump tapped from the fire pump feeder ahead of the fire pump controller with a local disconnect, appears to have appropriate grounding conductor sizes based on the provided ampacity. The utility transformer system's grounding is established using a 4/0 ground wire at the transformer. It is important to verify that the grounding conductors are properly sized according to the National Electrical Code, known as NEC, and local regulations. Addressing the question of establishing system grounding at all 3 services, it is recommended to do so. Even if an extended ground wire is connected from the transformer grounding system, establishing grounding at each service provides a redundant grounding path, crucial for safety in the event of a fault. Now let's focus on grounding conductor sizing. While the provided sizes for all 3 services seem appropriate based on ampacity, it is imperative to meticulously verify these sizes against the NEC and local regulations. The NEC provides tables and guidelines for determining the correct size of grounding conductors based on the size of the service entrance conductors. These tables take into account the potential fault current that the grounding conductor must be able to safely carry. Always consult the latest edition of the NEC and any applicable local amendments to ensure compliance. Now let's delve deeper into the NEC requirements for grounding electrode systems. The NEC specifies the types of grounding electrodes that are permitted, such as ground rods, ground plates, underground metallic water pipes, and concrete encased electrodes. When using a ground rod or ground plate, the NEC requires that the electrode be supplemented by an additional electrode. This ensures that the grounding system has sufficient capacity to dissipate fault current. The supplemental electrode can be another ground rod, a ground plate, or an underground metallic water pipe. In the case of the main service, the use of a ground rod in conjunction with the connection to the main water pipe is a common practice. However, as mentioned earlier, the 1/500 mcm conductor used for the connection to the water pipe may not be adequately sized. It is recommended to consult the NEC to determine the appropriate size of the grounding electrode conductor for the water pipe connection. Let's also discuss the importance of properly bonding all metallic components of the electrical system. Bonding ensures that all metallic parts are at the same electrical potential, which reduces the risk of electric shock. The NEC requires that all metallic enclosures, raceways, and equipment be bonded together to form a continuous electrical path to ground. This bonding is typically accomplished using bonding jumpers, which are conductors that connect the metallic parts together. In addition to bonding, it is also important to properly ground the neutral conductor of the electrical system. Grounding the neutral conductor provides a return path for fault current and helps to ensure the proper operation of overcurrent protective devices, such as circuit breakers and fuses. The NEC specifies the methods for grounding the neutral conductor, which typically involves connecting the neutral conductor to the grounding electrode system at the service entrance. Let's also address the specific grounding requirements for fire pump systems. Fire pumps are critical for fire suppression, and their electrical systems must be highly reliable. The NEC has specific requirements for grounding fire pump systems, which are designed to ensure that the fire pump will continue to operate even in the event of a ground fault. These requirements include the use of a separate grounding electrode system for the fire pump and the installation of a ground fault protection system. Regarding auxiliary services, the grounding requirements are similar to those for main services. The auxiliary service must have its own grounding electrode system, and all metallic components must be properly bonded together. It is also important to ensure that the auxiliary service is properly coordinated with the main service to prevent ground faults from affecting both systems. To summarize, proper grounding is essential for the safety and reliability of electrical systems. It is important to follow the NEC and local regulations when designing and installing grounding systems. Always consult with a qualified electrical engineer or electrician to ensure that the grounding system is properly designed and installed. Remember these key points. Firstly, establish system grounding at all three services for redundancy. Secondly, verify grounding conductor sizes against the NEC and local regulations. Thirdly, ensure proper bonding of all metallic components. Fourthly, ground the neutral conductor at the service entrance. Fifthly, follow specific grounding requirements for fire pump systems. And sixthly, consult with a qualified professional for design and installation. NEC provides tables and guidelines for determining the size of grounding electrode conductors based on the size of the service entrance conductors. For example, NEC Table 250.66 is commonly used for sizing grounding electrode conductors. This table specifies the minimum size of the grounding electrode conductor based on the size of the largest ungrounded service entrance conductor or equivalent area for parallel conductors. It's crucial to select the correct conductor size to ensure adequate fault current carrying capacity. The NEC also addresses the requirements for bonding jumpers. Bonding jumpers are used to connect metallic parts of the electrical system to ensure electrical continuity and create a low impedance path for fault current. NEC Section 250.102 provides guidelines for sizing bonding jumpers. The size of the bonding jumper depends on the size of the largest ungrounded conductor supplying the circuit. Proper sizing of bonding jumpers is essential for effective fault current protection. Ground fault protection is a critical safety feature that detects ground faults and quickly de-energizes the affected circuit. Ground fault protection is typically required for large services, such as the 2000 amp service mentioned earlier. NEC Section 230.95 outlines the requirements for ground fault protection of equipment. This section specifies the conditions under which ground fault protection is required and the performance requirements for the ground fault protection system. It's essential to comply with these requirements to minimize the risk of electrical shock and fire. In addition to the NEC, local jurisdictions may have their own electrical codes and regulations. These local codes may be more stringent than the NEC or may address specific local conditions. It's important to be familiar with the local electrical codes and regulations in your area and to comply with them when designing and installing electrical systems. Let's also discuss the importance of regular inspection and maintenance of grounding systems. Grounding systems can deteriorate over time due to corrosion, physical damage, or loose connections. Regular inspection and maintenance can identify and correct any problems before they lead to safety hazards or equipment failures. Inspection should include checking the condition of grounding electrodes, grounding conductors, bonding jumpers, and connections. Any damaged or corroded component should be replaced immediately. Connections should be tightened to ensure good electrical contact. In addition to visual inspections, electrical testing of the grounding system is also recommended. This testing can verify the integrity of the grounding system and identify any high resistance connections. Common tests include ground resistance testing and continuity testing. The results of these tests can be compared to previous readings to identify any trends or changes that may indicate a problem. When performing any work on electrical systems, it's essential to follow proper safety procedures. Always to energize the circuit before working on it and use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you're not qualified to work on electrical systems, hire a licensed electrician to do the work for you. Electrical work can be dangerous, and it's important to take the necessary precautions to protect yourself and others. Now, let's revisit the grounding of the auxiliary service. Even though the auxiliary service is connected to the transformer grounding system, it's still important to establish a separate grounding electrode system for the auxiliary service. This provides redundancy and ensures that the auxiliary service will be properly grounded even if the connection to the transformer grounding system is compromised. The grounding electrode system for the auxiliary service can consist of a ground rod, a ground plate, or a connection to an underground metallic water pipe. The size of the grounding electrode conductor should be determined based on the size of the service entrance conductors, in accordance with NEC Table 250.66. Also, it is imperative to understand the role of the equipment grounding conductor, often referred to as the EGC. The equipment grounding conductor is a critical safety component that provides a low impedance path for fault current to return to the source. This low impedance path helps to ensure that overcurrent protective devices, such as circuit breakers and fuses, will quickly trip and energize the circuit in the event of a ground fault. The equipment grounding conductor should be sized in accordance with NEC Table 250.122, which specifies the minimum size of the equipment grounding conductor based on the size of the overcurrent protective device. It's also important to ensure that the equipment grounding conductor is properly connected to all metallic enclosures, raceways, and equipment. Let's also consider the impact of harmonics on grounding systems. Harmonics are distorted waveforms that can be generated by nonlinear loads, such as electronic equipment and variable frequency drives. Harmonics can cause excessive current flow in the neutral conductor and can overheat grounding conductors. To mitigate the effects of harmonics, it may be necessary to increase the size of the neutral conductor and the grounding conductors. It's also important to use harmonic filters to reduce the amount of harmonics in the electrical system. Proper grounding is essential for protecting sensitive electronic equipment from damage due to voltage surges and transients. Voltage surges and transients can be caused by lightning strikes, switching operations, and other events. These surges can damage or destroy electronic equipment if they are not properly suppressed. Grounding provides a low impedance path for these surges to dissipate, which helps to protect the equipment. Surge protective devices, also known as SPD, can also be used to protect equipment from voltage surges. SPD are typically installed at the service entrance and at sensitive equipment locations. These devices divert surge current to ground, which helps to prevent damage to the equipment. In summary, grounding is a multifaceted aspect of electrical system design and installation. It requires a thorough understanding of the NEC, local regulations, and best practices. By following these guidelines and consulting with qualified professionals, you can ensure that your electrical systems are safe, reliable, and compliant. Remember to prioritize safety in all electrical work.